Hi everyone, we are project group number 21 and our final project is about predicting heart disease using statistical learning. We are a very international team. Imran is in the US, Tameem is in India, Paul is from Japan, and myself, Herman, is from Indonesia. This is the flow of our presentation. So we'll talk about project goals, dataset overview, EDA, feature engineering, modeling, and causal inference. Basically, we have 4 project goals. The first one is we develop a classification machine learning model to predict heart disease. And secondly, we have 3 causal inference analysis to examine like how does physical activity, various health conditions influence the risk of having heart disease? Does comorbidity like stroke, diabetes, kidney disease, or skin cancer increase the chances of having heart disease? And lastly, is there any causality between life habits with the risk of having heart disease? So with this introduction, I'll give to Tamin to talk about EDA and feature engineering. Thank you.
Thank you, Herman, for the introduction. This is Tameem Faruqi, and let me take you through exploratory data analysis and feature engineering. The heart disease dataset for the project was taken from Kaggle.com. The dataset comprised of 18 columns with heart disease as the response variable and 17 predictive variables based on demography, lifestyle, and underlying medical conditions. The data was collected in nearly 320,000 respondents. Among the predictors, there were 4 quantitative and 13 categorical variables. Luckily, there were no missing values. However, the outcome variable was highly imbalanced. In numerical variables, the pair's physical health with mental health and BMI with physical health showed strong relationships, while sleep time with mental health were inversely related. BMI was right skewed in the histogram. Majority of the respondents had good physical and mental health, and an average sleep time between 6 to 8 hours per day taken on the last 30-day period. BMI was treated for skewness by applying various transformations, out of which Box-Cox transformation gave a normal-like distribution. Out of 9 binary variables, stroke, difficulty in walking, and kidney disease seem to be strong predictors as the presence of the condition increases with proportion of the heart disease. Amongst non-binary categorical variables, respondents with age above 55 or poor general health or with underlying diabetic condition or Native American racial group seems to have higher chances of having heart disease. For feature engineering, we recategorize 4 predictive variables, age category, physical health, mental health, and sleep time into 3 categories each. Now I will give my colleague Imran to take over. Thank you.
The initial unbalanced naive baseline model achieved 91.4% accuracy but lacked any real value. After applying random undersampling for class balancing, the resampled model hit 50% accuracy, mimicking random chance. The area under the curve remained at 0.5. Using lasso-like logistic regression on balanced data, 7 coefficients were turned off, reducing encoded predictors from 37 to 30 for subsequent modeling. Utilizing these 30 predictors in a logistic model on balanced data improved accuracy from 50% to 73.5%. The AUC also increased from 0.5 to 0.84. Random forest classifier utilizing class weights and tuned hyperparameters improved accuracy to 73.8%, but AUC slightly reduced to 0.83. Implementing an ADA boost classifier model with tuned hyperparameters further enhanced accuracy to 74.15%, but AUC maintained at 0.83. Comparative analysis of confusion matrices revealed different strengths in different models. The statistical model excelled in true positives, which is critical for our problem statement, while ensemble methods were superior in true negatives. The logistic regression model emerged as the best due to its emphasis on accurate true positives and interpretability from a higher area under the curve. Lastly, adjusting classification thresholds to 0.4 as a sweet spot effectively increased true positives to 87%, but reduced true negatives to 63% as a trade-off, which is acceptable as the cost of true positives is higher than true negatives.
Hi, my name is Paul, and I'm going to go through the last 3 goals of our project, which is causal inferences. As you can see here, we're trying to understand whether there are any predictors that could be explained as the causal cause of our outcome variable heart disease. And we have grouped them into 3 different categories into 3 different goals. The first group is physical activities and health conditions. Second group is other diseases we call comorbidity. Number 4 is lifestyle. And by the way, we are using the Python package PSMPY, and we'd like to move on to our final conclusion. Our conclusion is that we, after propensity score matching, we did not find any predictor to be the potential cause of our outcome variable heart disease. And there is a little caveat here where we actually realize that using a subcategory of a general condition of health or mental or physical actually is not the correct way of doing it, and therefore we like to look for ways to overcome that in the future. And finally, as a side note, we ran into memory problems, which we would like to find, maybe move to the cloud to be able to avoid that. And so that concludes our presentation, and thank you very much for listening.